Hi, my name is Sharbil Tog. I am an assistant professor of mechanical engineering at the Lebanese American University. Today, I will share with you our research work on 3D printed soft grippers featuring soft pneumatic fingers with local bending joints at the 2024 IEEE ASME International Conference on Advanced Intelligent Mechatronics in Boston. The research objective of this work is to develop directly 3D printable fingers with local bending joints that require no post-processing using low-cost and open-source fused deposition modeling 3D printers. Introducing localized bending joints enhances the deformation behavior at lower actuation pressures and provides a linear relationship between the input pressure and the output deformation and input pressure and the tip force. This linearity is very important for directly controlling the actuators using simple controllers such as proportional integral derivative controllers known as PID controllers. Also, integrating such fingers into soft grippers enhances the gripper's grasping performance and reduces the risk of slippage as demonstrated in this work. The design process starts with modeling and designing the soft fingers in a way that they can be 3D printed using a low-cost and open-source FDM 3D printer. The 3D printing parameters are optimized in the slicing software to obtain functional airtight soft fingers. In addition, in the same design process, we characterize the soft material used to print the fingers to assess its stress-strain behavior and to develop a hyperelastic material model for use in finite element modeling. Finally, the fingers are characterized in terms of their experimental deformation or bending angle and output force at different applied input pressures. And then the experimental data is used to validate the FEM data. The soft fingers are based on a pneumatic network design that is optimized using FEM along with the local bending joint, not only to lower the stresses and strains at high input pressures, but also to generate large deformations and forces at low input pressures below 60 kilopascals. A commercially available soft thermoplastic polyurethane, or TPU, known commercially as NinjaFlex, is used to print the soft fingers. The soft fingers can be used to build soft grippers with multiple configurations, including two-dimensional, single-stage, and double-stage grippers, and three-dimensional grippers as well as multiple stages. This makes such grippers not only modular and versatile for pick-and-place applications, but also have multiple degrees of freedom since each actuator in a multi-stage configuration can be actuated separately. This approach enhances the grasping performance in some scenarios as demonstrated in this work. Highly nonlinear finite element simulations that involve geometric, material, and contact nonlinearities are performed to predict and optimize the performance of the soft fingers in terms of output deformation or bending angle and output force before their fabrication. In addition, finite element simulations are used to design different topologies for the local joint to make sure that the minimum stresses and strains are exhibited at the highest input pressure. This step is essential to make sure that the 3D printed prototypes are durable and reliable by experiencing low stresses and strains. Moreover, FEM simulations are used to obtain a linear relationship between the input pressure and output deformation and force. In terms of bending behavior, two designs are simulated, where the first design does not incorporate a local bending joint, as shown, and the second design includes a local bending joint, as shown as well. A linear relationship is obtained between the input pressure and the output bending angle at different input pressures. The inclusion of the local bending joint shows that the deformation is localized and the actuator does not curve as in the first design that lacks a bending joint. In terms of output force, the same two designs are simulated as well. A linear relationship is obtained between the input pressure and the output blocked force or tip force at different input pressures. The bending joint had little effect on the force. In other words, the force output was not compromised by the addition of such a joint. The actuators generated forces higher than 5 newtons at an input pressure of 6 kilopascal or 60 kilopascal. The actuator is experimentally characterized in terms of output bending angle and output force, and this experimental data is compared with its FEM counterpart. There is a minor difference between the experimental data and the FEM data, proving that the finite element models are accurate to predict and optimize the performance of the actuators. The bending behavior of both actuators is also very similar as shown. The actuators are also assessed in terms of deformation hysteresis. They exhibited minor hysteresis that is very acceptable for a soft actuator made of a soft 3D printed TPU. Separate 3D printed soft fingers with local bending joints are used to build two-dimensional single-stage and double-stage grippers. Here, each stage is actuated separately. The different configurations can grasp different objects with different weights, sizes, shapes, and textures successfully. One important thing to note here is that actuating a certain stage without the other stage of the gripper can adapt it to different shapes more easily and allows it to grasp different objects successfully. For example, in figure F, where the two stages are actuated, the gripper performs a pinch grasp to pick and hold the tape. This pinch grasp is not ideal for grasping a flat plate as shown in figure H. So, to enhance its grasping performance, only the first stage is activated as shown in figure H. This results in a higher contact area and a more stable grasp. Therefore, the behavior of the gripper can be tailored for different pick and place tasks in order to grasp different objects successfully. In this work, a soft gripper is designed and developed based on 3D printed soft pneumatic fingers with localized bending joints. The introduction of localized bending joints enhances the deformation behavior at lower actuation pressures and provides a linear relationship between the input pressure and both the output deformation and tip force. This linearity is crucial for directly controlling the actuators using simple controllers. Finite element simulations are used in the design process to optimize and predict the behavior of the soft pneumatic actuators in terms of deformation and tip force. The soft pneumatic fingers are demonstrated by showing that a gripper with different number of fingers and stages can grasp a wide variety of objects with multiple shapes, weights, textures, and stiffnesses successfully. This work was supported by the Lebanese American University. For more information about our soft robotics research, please check my YouTube channel by scanning the QR code shown. Thank you for your time.